Nice. Okay. All right. Let's start. So I'm Thomas. I work at the EF in the Robust Incentives Group. I am a bit of a disclaimer. I'm not a P2P networking guy originally, so I don't expect like a deep expertise in this. But I got nerds typed into like thinking about this problem a few months ago, and I want to share some thoughts about what I've been working on, basically, and how that fits into the maybe more general Lean P2P picture. Okay, so if we try to start from first principles, there is like this sort of like very simple question we can ask, which is how can messages be propagated efficiently across a network of nodes? And so when you ask that question, you have so many answers. Like it's been studied by so many people in so many disciplines and domains that it becomes a bit vague, and the literature is actually not that easy to parse. And it's also like, yeah, it's not a simple problem either. Like even if you like ask that question, it's sort of like too abstract to be taken seriously and sort of make progress on it. So what do you do when you have vague questions? You try to add constraints, I guess. And we have so many constraints. Like as you guys know, like Ethereum is like a very sort of like constrained environment, and we want the network to be decentralized. So, for example, we don't have like a sort of like global view, bird eye view on the network at all. So we only have like partial local views of the network. We have like very strong bandwidth and hardware requirements. So we need to deal with that too. People can attack the network. So we need some sort of like robustness against this as well. Yeah, the network is also not stable at all. It's changing all the time, and what you optimize for today might actually change tomorrow. Then we also want privacy. I don't think we are doing too great now. My take is like we should get towards more privacy instead of like, I mean, some advocating towards like less privacy and more optimizations or efficiency. I think like privacy is still very important. And we have, yeah, different types of messages being propagated all at the same time. All like we have validators and nodes doing so many different things at the same time that it's not always easy to deal with. I think I'm fine. Yeah, thanks. So yeah, so when we have these constraints, I guess you can just like do our favorite thing to do in Ethereum is like come up with trilemma. And so here's one. It's not an official proven trilemma, so it's just like one that makes sense to me. I think you do have some sort of trade-off space, and you can get like a very sort of like super efficient, very simple, maybe also like way of propagating messages. If you have like a super stable network, centralized infrastructure, and it's easy. It's not very resilient though, because I don't know, if you take down the server or the entity, then it breaks. And yeah, you can sort of easily get like two of those dimensions to work pretty well, but like once you have the three together, it gets harder. So one dimension is leanness or like simplicity. And today, I don't think we are like doing really good on any of these things, unfortunately. Like I don't want to be like too harsh either, like, but yeah, like the resilience is kind of good. We'll see, like at least it's sort of robust in the way we propagate messages, which is nice. But the privacy, for example, question is still like not perfect. It's not. I will argue it's not very efficient, and it's not that complex. It's not like super not lean. Like for example, the way we propagate messages is like just send it to 8 random peers. But it's not like simple when you sort of like put it all together. Then it becomes extremely complex, and it's hard to like keep track of all of it.
Just a quick observation on this. There's a certain resemblance to the traditional tradesman's triangle, fast, good, cheap. So maybe that offers a bit of evidence that this is a trilemma.
Okay, all right. Well, I'll take it. Good trilemma then. Thanks. And then, okay, so when you look at it from sort of like an outside observer perspective, you want to know where to start. Because we do have like different propagation mechanisms, where you have this sort of Igor push that is like the most expensive sort of like, yeah, you need to propagate one message across like all nodes. And then you have like this sort of like fallback of lazy gossip of like using the I don't want and I want messages. You have two layers. So I mean, yeah, you need to deal to like two p2p networking stack in parallel, which is not ideal. And then, of course, yeah, again, message heterogeneity, and then, yeah, difference between global topics, subnets, and everything. So, yeah, I think it's hard, for me, it was even hard to like engage with. Like you come in and you see all of this and you're like, okay, how are messages propagated through the network? Like that feels a bit crazy. So I will focus on the one I was not sniped on, which is the eager push. I think I focused on this because it's interesting, but also because there is potentially like a lot of efficiency gain to be had there. So that's sort of like mostly what I focus on. But we'll see how it ties to everything else, because like everything is sort of like interconnected, right? Like you can do like an eager push to like all different kinds of messages that can be across the EL or the CL. So yeah. And then you can ask, like, you even need like a lazy gossip fallback if you have like a really good eager push. Like, so yeah, you can actually like sort of like interrelate everything. So yeah, very lean. I think you've seen this meme before, right? The idea is, can we find like a really good rule that I will want to call soon, because I like it, and then I'm trying to like fit words to match it, but we'll see how well that goes. But yeah, the idea is to like, can we actually get one rule, maybe with like we'll see like with a knob to trade off like efficiency versus latency, that we can use like across the p2p stack for this sort of like first eager push mechanism. So that's what I'm going to talk about. Yeah, so that's, I'll go quickly because it's not super. Well, actually, some of it is actually very important. But yeah, we model the network as like a weighted graph. And so, yeah, nodes are nodes, which is nice. And then the round trip time, so RTTs, are on edges. So, you know, the distance between two nodes will correspond to like the round trip time between these two nodes. And then for the topology, we actually treat the graph as a fixed random graph. And that was to try to mimic the peer scoring sort of setup we have, which is, you know, we downscore peers if they do something bad, but we don't really like sort of like connect to peers because they are faster or anything. So it was trying to like sort of mimic this kind of randomness of like having, you know, a set of like maybe 50 peers you are connected to, but like without like an actual sort of like big heuristic around why you're connected to them, other than they are acting, they are behaving okay. And then local decisions, like you don't have this sort of like bird eye view, so you need to like deal with what we have. So each node will only know about RTTs from its connected peers, which are 50, and you don't have like this sort of like global optimization problem, which is actually also difficult to solve, but yeah. Okay, so what do we try to optimize for in the setting? Bandwidth, and it's just like average duplicates of the same message received by a given node. Then coverage, like how many % of nodes in the network are actually informed, so get the message in the first place. And then the latency, so that's just like the time to reach, I don't know, like 90% of nodes. And that's the sort of like metric we use across our simulations. Okay, yeah, so again, what we have today, we have a mesh of like 50 scored peers, again, like using this sort of like peer scoring rule I just talked about. The eager push is to just 8 random peers, and that's what we are going to focus on. And we have this lazy gossip fallback that I already talked about. And so the pros is like, yeah, the random push is like pretty robust, like actually really robust, I would say, because it is random, so you can't like really trick nodes with like fake information, which is very nice. the coverage is also good because, you know, if you like send to like 8 random peers all the time, like you will reach like a very sort of like high coverage eventually. And the latency is not too bad. It's not great. Like you can do better for sure, but it's not terrible. And like you end up like reaching a high percentage of nodes in not a super long time. I think the big bad thing is like bandwidth inefficiency. Like the fact that you just like forward to random peers all the time means you receive a message so many times, like the exact same message, which is obviously not great. And again, like the leanness is, I don't know, I put it in the count, but it's not that complicated. It's just when you combine it. Yeah.
Just one thing.
Yeah.
Technically speaking, the eager push is not really to 8 random peers, but rather peers that have been scored highly, which is a factor of several observations we make, including the time to first delivery from every peer.
Yeah.
So it proxies latency in a way.
Yeah.
It's more informed than just randomly like selecting.
Yeah. So 8 random peers amongst the 50 scored peers. And in the peer scoring rule, you have some elements of latency. Is that what you're saying?
So
would you mind taking the mic?
Thank you. So really, can you hear me?
Down.
No.
Bottom. Put the knob.
We good? Yeah, whatever. So in reality, so Gossip Hub has multiple topics. There is a mesh for every topic.
Yeah.
The degree of that mesh is 8.
Yeah.
The peers that we score are those peers that support Gossip Hub and share topics with us. So, which is basically everybody that is part of the network. And that depends on the configuration of the client. So every client will have a optimal value that they shoot for peering with X peers, right?
But it's around 50, no? Oh,
no, so 50 would be the target of the EL.
Okay.
Yeah, and for example, the Prism has a default configuration of 70 peers as max peers.
Okay.
And usually, depending on the type of the node, operators will increase that value to something higher, usually. So in reality, you're peering with usually more peers that support Gossip Hub, but you're only selecting for each mesh and for each topic that you're subscribing to. You're only selecting 8 peers.
Right.
And those peers are selected based on their scores.
Yes. Okay. Yeah. Okay. And there is a component to latency in the score.
Exactly.
But it's quite.
It's a secondary. It's kind of like a second degree.
Right. Okay. That makes sense. That's a good call. I think I saw at one point that there was some latency into it, and I was like, okay, that seems to be like not driving like the main sort of like driver for connecting to people.
Yeah. So just one thing there. It wouldn't be link latency as observed. It's actually time to deliver the first copy of the message. So every time that we receive a unique valid message that we expect, that we validate, and is the first copy that we receive, we bump up the score of that peer.
Okay.
So in reality, it's kind of like your dissemination time within the centrality within the graph.
Yes. Okay.
But with a caveat that the producer is always
moving around.
Right? So really, you don't have a good centrality. Like absolute centrality measure.
Yeah, it's rotating centrality.
Exactly.
Yeah. Okay. That's cool.
Question: How cliquish are these peer groups?
That's a great question. So there is churn, and they tend to be somewhat stable. We're trying to get a good measurement of what is the churn of the graph in general. So I don't actually have a good answer right now, but there is rotation.
So let me clarify my question. I'm trying to get a sense of, given 2 peers, what percentage of peer A's peers are peer B's peers?
Right. We don't have a good number on that. We do have raw data, right? Like as of 1 month ago, that we are analyzing currently. So hopefully there's a team, ProBlab, shout out to ProBlab. They're using this raw data to actually apply a model and to understand how the graph is churning, how the graph is dynamically changing over time. So I think we'll have some numbers ideally in this week or maybe next week. And yeah, I think that's going to be very useful to make decisions.
Nice, thanks. Yeah, I think I mean, one of the things that is listed at the end of my talk is like the interaction with the peer scoring rule, because I do feel like it's super important, but it's complex to like even like sort of like think about right now, because like you have like so many little elements that go into the peer scoring, and so basically I think there are more like two questions, like you want to optimize the peer scoring and like peer selection in the first place, like and go full in, or do you want to keep it somewhat random? Yeah, those are like open questions.
And perhaps to add to that complexity is that that scoring is applied, if I remember correctly, to all topics equally.
Yeah.
Which every object in Ethereum actually has a very different propagation path and characteristics.
Yeah.
And also the parameterization of gossip stuff, the parameters are actually shared between all topics. So,
right, okay.
And that is that could change for implementation.
Yeah.
And that's totally fine because it doesn't break the standard, the spec.
Yeah.
But no implementation, as far as I know, is able to tweak per topic parameter.
Right, okay. That makes sense. Cool. Okay. Great. So yeah, for simplicity, I did model it like this. So simulation of like you're connected with like 50 random pairs and you just forward to 8, and you have like sort of a plateau. You can't forward to more than 8, but we'll see that depending on the rule you use, you might, in some cases, sort of have like this adaptive threshold that you use to not forward sometimes. Okay, so yeah, we ran some simulations to get an intuition of like what we could even think of as like better rules. And so yeah, that's what we use. We had like 1,500 nodes in the simulation. We used the mean degree of 50 again. And then yeah, for the RTT distribution, it actually matters, but like right now we just use like a log normal sort of like distribution that is like sort of like nicely shaped, and we go with that. But I will come back to this because it's important. And then for the metrics, I mean I already said it, but like we do measure just like the average duplicates, the coverage and the latency we set to 90, just as like a sort of like guiding principle of like you need to hit more than 90% of nodes to like reach the coverage floor, and latency was measured as the time to reach 90% of nodes. Okay, so I think one thing that's extremely obvious to everyone, but like you have RTT awareness that plays a big factor, right? Those are like two strategies or rules that don't use RTTs at all. So the one we have today, which is just like simplified forward to just like delta neighbors uniformly at random up to 8. And then the coin toss will be like, just propagate to each neighbor independently with probability P, and you can just like, I don't know, sweep across that P probability to see what you get. So those, I mean, you'll see are not like super efficient. And then we thought of like two main RTT aware rules. So the one is very simple, like delta fastest, just like propagate to the fastest neighbors you can, to the 8 neighbors that are like the fastest basically, with this sort of like smallest RTT out. And downhill is, I'll stop like just a bit on this one because the rule is forward to nodes that have an RTT out that is like lower than the message you just received. So if you receive a message and it takes like 100 milliseconds to receive it, you'll only forward to nodes that you are connected to that have like a smaller RTT, that you have a smaller RTT with. So this is sort of like, that's why I called it downhill. The other like term I use is WFR, but that's outdated. But basically that came from having this idea of this very known problem of optimal transport, where you try to move mass across like nodes in a graph. And one of the sort of like optimal way to do this is just to like have this sort of like gradient descent rule, and that's what that's where the inspiration came from. But so yeah, how is it doing in the simulation results? So the first thing is that I don't know. So for the two, RTT unaware rules, you get like good coverage, like quite fast. So you have like the coverage on the y-axis and then the duplicates on the x-axis here. You also get like really good coverage. We can't really see it, but like with the delta fastest, it actually covers like a lot of ground. But it's really struggling with the downhill rule, like here. It's like because it's like you try to forward like going downhill, but like given the properties of the graph we are dealing with, like you hit like roadblocks, so you can't like actually propagate that message further, and you just like get stuck in like local minima. So that was interesting to see. And then for the latency, so downhill is not even plotted because it didn't reach 90% of nodes, so it doesn't like hit the sort of like floor. But what you can see that's interesting is like you do get a very big difference in latency when you compare delta fastest, so like just send to the fastest peers, compared to like random or coin toss sort of like rules. And so that's one takeaway. It's like, okay, it does look like we, do pretty well on coverage for all of these except downhill. But I'll come back to this. But when it comes to latency, we can do much less, like much better latency, but also with like lower sort of like duplicates if you just have this extremely dumb rule of like propagate to delta fastest peers, which is sort of nice. One of the problems with the delta fastest, I'll come back to, is like the only knob you really have is to how many peers you send it to. Like, if you want to like lower the number of duplicates, you just have to like send to less peers. So it's not a great way to like deal with the sort of like trade-off you want to make between duplicates and latency. So we try to go for better rules, I guess. And one thing that's super important is the realization that there is this really cool feature of having a sort of like random set of peers. First, it's robust, right? It's hard to trick, but it's also like at one point you hit like a percolation threshold. And so if you send to more than n peers randomly, you will hit coverage because it like propagates and like the message can actually reach all nodes at some point, which is very nice. So the idea was like, okay, can we use like this random backbone and add on top for the like remaining peers like very optimal sort of like efficient rules. So that's what it's showing basically. And so you look at delta fastest, you look at downhill, and you see how downhill was doing very, very bad on the coverage side without any random backbone. But at some point, it just like reaches like almost perfect coverage, just because you add some like random peers you actually forwarded to. And for delta fastest, I mean, it doesn't really need the backbone to get coverage, but like it always just like consumes the maximum bandwidth you can ever think of. So here you can really sort of like see a whole area between like downhill that is extremely bandwidth efficient, but that sometimes doesn't really hit coverage, and isn't doing as good for latency as delta fastest. But so basically you have this whole area here and here that you want to be able to like sweep across that area, right? And you want to be able to optimize between, do I want my messages to be propagated very, very fast, or do I want them to be like using as low bandwidth as possible? And so what you can do is do a hybrid rule. And so that's what I'm like trying to advocate for, because I think it makes sense. The first step is basically to set a random backbone, so you're sure you hit your percolation threshold. So you can see in many simulations that it's always like 2 or 3. like after that, like you actually hit like decent coverage in like decent latency, just like we have today with like the sort of like gossip sub forwarding to 8 peers. And then for the rest of the peers, you can just like try and optimize for what you're looking for. And we thought of 2 ways of doing this. I think those are like nice conceptually to think about. The first one is like absolute threshold. So you only forward to a node if the RTT out is under a certain arbitrary sort of absolute set threshold. And so that mimics a bit, it's a bit different, but like still conceptually a bit like reducing the number of peers you send it to, like doing delta fastest, but just like reducing the number of peers you want to choose. And it's a global threshold, like sort of like applied to the entirety of the network. And then you have soon, which is, okay, you have set that random backbone, but then you can, do the RTT out inferior to RTT in, but you can have like a boost of that to allow more or less peers to be including based on what you want to optimize for. And so what you want to do there, and so you can see that it's much more local because it's always based on like the message you receive in the first place. Whereas like absolute threshold T is more like of a global sort of like, okay, no, I don't want to like send it to too many peers, so I'll just like shut it down. And so you have like a very sort of like, you have very different rules. And we looked at what that gives in simulations. The idea is always to choose the threshold or the slack as is for slack, but it could be anything, it's just like a parameter. And yeah, the idea is to choose like how to set those things based on the sort of like preference along the latency bandwidth spectrum. Yeah, so that was again like the sort of like setup we used. And in this setup, like we actually see that Soon is not doing much better than Absolute T. Like the performances are like, Soon like doesn't really reach like perfect coverage. Like it does pretty okay, but it never like truly gets to 100%. And then for the average duplicates, like it's better when you have like more slack in your T, obviously, because it's better when you have more slack when you have more slack. But in terms of latency, you can see that Absolute T still does quite better than Soon. So, and it's hard to parse, so you can do this. And here, like you basically match the bandwidth you are looking for between the two rules, and you see that Soon like always sits on top of Absolute T. So that means it's doing a bit worse, basically, than just having this global threshold. And so that's interesting because we actually noticed that if you change the the RTT distribution of the network, and you now have like a bimodal distribution, which could be the case in like real world networks, because you can have like sort of like clusters based on geographical distributions or even ASNs or anything. Then it's completely different, and then you have like much better performance for something like Soon than something like the global sort of like absolute threshold, just because like, for example, you never really reach all peers in this sort of network because like some peers will always be excluded from your maximum threshold. You always have to consume like the maximum sort of like latency, like you always are like at 300 because you always send to 3 peers with the backbone randomly. And you are doing like a bit better in the bandwidth, but like overall, like the trade-off is really much worse for Absolutely compared to Soon. Yeah, and you can see it here. Like, basically, having an absolute threshold in like sort of like a more heterogeneous network, like gets you stuck in sort of like regions you can't like really get out of. While Soon, because it's adaptive and local, can actually like sort of like do quite well, even if you have like a different sort of like network structure and also like RTT distribution, basically. Okay. So you see that those are like literally like super early exploration. Like I was running these simulations last night, so don't take it for like a super like extremely well established sort of finding. But it did feel like as soon as you change and you depart from a very sort of homogeneous network, then absolutely like just like struggles with it. And having these sort of like global thresholds on the network is just like not really good. And when you just, I don't know, you go from random networks to like small world networks, or you change a bit the RTT distribution based on geography or whatever, and soon like always sort of like performs better in this context just because of its local adaptability. And yeah, so the idea I want to like try to shield, but let's see if it works, is like basically you can use the soon rule and use slack S across like the latency and bandwidth sort of like spectrum. So if you want very fast message propagation because it's like in the critical path and those are like small messages, for example, then you can like, I don't know, just like have a lot of slack, and it will converge to having this sort of like delta fastest rule that is just like always super fast and optimal for latency, for low latency. But if you have like very big messages and you need to like avoid like messages getting sent like super many times to the same nodes, then you can like tune slack towards a more like downhill thing, and you'll always hit coverage because you have like the random backbone, but at least you'll be very efficient in how you spend your bandwidth. And so yeah, ideally you could like use that same rule and tune this sort of like knob to like, yeah, to be suited for different types of messages across the network. So yeah, I think what we really need, as you've seen, is better observability, because if the propagation rule actually depends on what network we have, then we need to know like approximately what network we are dealing with, so we can actually make like informed choices about the rule we want to use. So I think some empirical data collection I think is going on already. But I'm very curious to just like get these RTT distributions and get a more like granular idea of the topology of the network, so we can actually inform these choices. Then yeah, I'm planning to just like run more realistic simulations. I think those were all like Python just like simulations, and I think we can do way better with like running like libp p2p binaries in Shadow. And yeah, I mean, at the same time, we'll continue exploring. I think the next step will be DevNets, and then like try to ship it. I don't think like this should wait for in Ethereum at all. I think like if we can ship it and we have like high conviction, it's like a good thing to do. We should do it soon. And yeah, that's what I was saying like before. I think we had that discussion about like how it actually interacts with like the peer scoring rule, and the lazy gossip mechanism is actually interesting to look at. And a sort of like second thread that Marius, that joined DF recently and has been working on this with me, by the way, quite a bit. I don't think I mentioned him at the beginning. Is can we actually prove formally sort of like near optimality for a given rule? So then we can just like move on and use that rule and just like be done with it, and not like spend like iterate again and again on like finding some like different mechanisms for propagating information across the network. Yeah, thank you. You guys have questions?
I do, but I've spoken a bit, so I want to see any thoughts before I guess not, so I'll take it. So a couple of things. I think this is so latency sensitive gossip is very interesting. As I said, we're gonna like incorporate it right now as incorporate RTT, but not really RTT. It's actually just like speed of dissemination, how fast we get a particular message in a word scoring metrics. So in a way, it's already there. The thing, I think one important factor, background parameter in all of this is the graph, the site, like the topology of the graph that you've that like the simulations have been run with, because in reality, peers, like what is the strategy for a specific peer to connect to other peers in the network? What are you generally like in an overarching way optimizing for? Because in local like heuristics like this, you will be sensitive to like what the overall strategy has been, right? That's one thing. Second is I do think that there is value in pushing messages to peers that are actually far from you. Because especially if you're the unique producer of a message, right? Because so as the first publisher of a message, that gives you an opportunity to start disseminating the message ahead of time in other geographies that are far from you. So I do think that like the space is really nice. One solution variant here that I'm interested in exploring is bucketing. By distance. Which obviously has its own problems because it can be gamed, because a peer can always simulate that they're further away from you than they are, but then you can incorporate heuristics like does the latency match the geolocation of this IP address, for example? It does get complex, but you could detect scenarios like that. I don't know, it's just kind of like an idea.
So maybe just on this, because I do think it's interesting, and I've tried to thought through it as well. It's like both. I mean, if you do it with the IP address, for example, then it's not very private. Like you lose some sort of like privacy, I guess, and that's maybe not ideal. I think the bucketing itself is also like hard to do. Like it will be somewhat hard. Like I don't know exactly how you choose which buckets, how many buckets do you have, and things like this. And I do think there is a lot of value in propagating to peers that are far from you, in the sort of RTT sense of the term. But I think what Soon somewhat optimizes for, sometimes at least, is to send information quickly through peers to reach like nodes that are like sort of far. So it's not like it's not like, you pick someone that is far, but like if you have like a good way to, like a fast path to nodes that are like sort of like in further geographical locations, I think that also might be another way to like sort of like think about this, instead of having some strong assumptions about like who is where and everything. But I do think it's like interesting. Like I think we should explore it for sure.
We should definitely continue discussing this. Two more like top level thoughts here. Are for large messages, specifically these kinds of gossip protocols where you need to receive the full message and validate it before you act on it. The store and forward kind of like protocols are quite inefficient for large messages. And it's kind of like one of the bottlenecks that we're hitting with larger blocks and larger and higher gas limits, which will naturally lead to larger blocks. So the solution space that is more appealing is the one of erasure coded broadcast, chunk and so on. So I think that would be like an entirely different paradigm.
I think, so it's, I mean, I agree. I do think that this is sort of like agnostic to how large, I agree that we should like sort of like stop, like avoid having large messages generally. Like I feel like that's just bad. But that rule is agnostic to whether that is big or not. It's more about like, you want to save bandwidth or you want to like just fast propagate it through the network.
It kind of like the routing strategy is a little bit independent of like the content of like what you're sending. So I agree that like this would be on the routing, strictly on the
exactly.
Then one other thing is that right now the network is actually flat and permissionless, which means that any node that you spin up, specifically any CL node, even if it's just for testing, is going to have the opportunity to join the network and actually influence propagation. And that is one major like limiting factor for us. And there are solutions like, for example, the crypto team worked, and like some people here have already discussed it, like already aware of this. The crypto team at the EF has made some progress on proof of validator.
Yeah.
So that's a primitive that we could potentially use to prioritize peers that are actively securing the network over observers of the network. So that would constrain the graph even further.
Yeah.
Right? If we were, or like even bucket it further, because we do still propagate to peers, but they just to peers that are not validators.
Yeah.
But we just deprioritize them.
So I think that's great. I do think it's a bit also different, but what is just like what some of the things you are telling me are just like for me confirming the fact that we need to have like very different buckets, and I feel like the last part could be in the like, sort of like peer scoring part of things, right? It's more like how do you prioritize peers you are connected to? How do you even connect them to them in the first place? How do you like sort of like construct the graph of peers around you? And then how do you push? And those things are obviously interrelated, but I feel like it's nice conceptually to think about it separately, so we can really like sort of like optimize for both of them and then like look at them together.
So just to kind of like put some more context there, right now implementations have a connection table basically, and that connection table is scored linearly based on a number of parameters that are set by the protocols themselves. So for example, if the more topics you share with another peer on the gossip sublayer, the higher the score will be for that particular peer. Things like that. Then you will naturally like score peers that have higher that have an overlap in your adnets, for example, over peers that don't, right? But this is a very naive way, because in reality, what you really want to do is segment the connection table into different purposes. And say, I want to find the best peers for block propagation. I want to find the best peers for column propagation. I want to find the best peers for for each of the adnets that I'm subscribed to, and then even that rotates on XFox, right? So it's kind of like a more purposeful way of peering with the network, and that would like be kind of like the background thread in all of this, because then you would be having meshes that are optimized already for a specific purpose. With some of which might actually be using erasure coded broadcast, like in the case of blocks in the future. So then like it's kind of like thinking more about fine tuning for the specific scenarios.
Scenarios and messages. I feel like that's also. I mean, we've talked about this. I think a bit, but like I think the idea that you already had is like, can we like tailor it to a particular type of message? And I think then, just like another thought, I guess, is like to be careful about not overfitting. Like when you tailor it too much, then you lose the leanness, right? Like you lose, like you actually will like sort of like really sort of like put a lot of constraints, so you optimize a lot for one particular thing, but then like then you don't want to do that for like every specific scenario you can think of, basically. And
you lose resilience, right? Because the more specific you get, then you're overfitting for like some scenario that like you've designed, and if something changes,
and things change all the time, right? So if like
so you need to stay adaptive. That's really important.
Yes.
Did you run simulations for the network like size, maybe 1,000 validators, something like that?
That was 1,500. So I was very small.
Okay, and basically, like, how faster is that if we use Soon comparing to just randomly choosing our neighbors? Like, do you have this?
I didn't put it in the slide because I went with a progressive approach, but this gives you it's not Soon, but like Soon converges to k fastest for latency and bandwidth, and so you see the sort of like random is this line, and k fastest is this. So it's not soon, like soon can be tuned to like be like k fastest, delta fastest, but you see like basically what you see here is like you can go for way lower duplicates with very good latency with something that's RTT aware compared to anything that's like random or like not RTT aware. So you do get to like, I don't know. Generally, what I saw is like a 40% improvement
40%.
in terms of like bandwidth efficiency. So like lower duplicates for the same sort of like latency, or like just better. It's just like depends what you choose in the trade-off spectrum. Again, if you really want to optimize for latency, you set soon with like a very large slack. You get to delta fastest, and you get like the best latency you can even think of. You'll just have like a lot of duplicates, but not more than random. So it's just like a better rule that can also be tunable, but like, yeah, you get the near optimal latency for the same number of duplicates, basically.
Yeah. Just one of the tasks that we have here is that how we can come up with the best topology, for example, for signatures aggregation, and even speaking about the subnet level where we have like 1,000 validators and we need basically everyone. Well, we kind of have different ideas, but one of them is that we need everyone in the subnet to actually observe as many signatures as possible. Maybe for example 90% threshold that you have here. I'm particularly curious like how faster we can do this with something like soon comparing to just randomly selecting neighbors, for example.
So we can implement it and check.
We can implement it actually. Well, we have simulation for the aggregation. We use like real world latencies from the RIPE database. Maybe you also used it.
I used it too.
So basically maybe we can update. I was thinking maybe we can update our simulation so that before we actually run the simulator, we not just randomly assign neighbors as we do it now, but since we are aware about the latencies, we can also calculate the most optimal neighbors according to soon and compare. But honestly, I mean, we did so many optimizations on COSIP-SAP, and we tried different ideas, and the improvements were so little. Which is why I was asking, like, how much gain do we expect? Like, is it orders of like 1-2% or 10-20%?
No, it's
the gain. I mean, how faster we can reach our goal, which is like send up signatures many to many, like everyone observes every signature.
I think the improvements are actually quite good in terms of latency. So pure latency, like random doesn't do too bad. It just like spends a lot to get there, basically. So when you have, for example, if you have super small messages, like very small, then like using random and like delta fastest or like the latency optimal sort of like strategy won't make a huge difference. It's more like as soon as you have some messages that are like quite large or whatever, then
3 kilobytes.
What?
3 kilobyte message.
3 kilobytes. Yeah, I mean it adds up, right? Like it's if you receive like 8 duplicates of each message, like of 3 kilobytes, like, and that's it's just like added load generally. So I think I think what I'm saying is like you can get to like way lower duplicates per node with the same latency, and you can like improve a bit the latency, but like the most important thing you're going to get is like less duplicates, because it's going to be smarter about how to, like, what peer to send it to. And sometimes the heuristic you will use will be like, okay, for sure that peer has received it already, so I don't need to send it to him. And so that, like, you won't send it to that peer, and that peer will like be better off because he will probably have had this message already, so he doesn't need to like get a lot of duplicates, basically. So yeah, I think, I mean, if you want, like, we can try, because I don't think it's, so if you have RTTs like, if you have like knowledge about RTTs in what you're like testing, then it's very, very easy to implement. It's just like that rule is so easy. So we can also like try it out and test it in like more real life environments and see how it does. But I expect it to do quite well.
So if I can throw in a suggestion here, so we're trying to minimize, at least in my mind, the trade-off here between latency versus bandwidth. We'd like to approach the best of both worlds, and to some approximation that would be given by optimal solutions to the degree diameter problem, which is the problem of how do you have a connected graph with as few edges as possible and the shortest maximum length path, right? If that makes sense.
Yeah.
But like this is actually kind of an easy problem if you have a global view of the network and some centralized entity can assign the connections between the nodes. So
Yes.
I think the like a question worth exploring is, are there rules by which each individual node can decide its neighbors in such a way that approximations to the best known solutions to the degree diameter problem arise organically out of that.
That's exactly right. Like that's how I got pulled into this. It's because I was talking to this guy that was doing optimal transport, which is how to provably move mass across a network of nodes in the most efficient way possible. And that's been a problem studied for many, many years. And so he was telling me about this, and I was like, oh, can that apply to P2P networks as like a sort of like random thought? And basically there's this whole like newer, because it's math, so it moves slow, but like literature on unbalanced optimal transport, in which you can also create and destroy mass, which will map a bit better to P2P networks, because you have deep duplicates and you can also like just like stop sending messages. And then there was this new literature about like, so they call it like a splitting scheme or whatever, but like is how to approximate this, because like all of this is using a global view. Like your optimal transport is like you assume that's part of like the initial assumptions and you never like think of it again. But there was this new work of like how to approximate this sort of like efficient way to do that in using a global view with local rules. And so that's like a new sort of like unbalanced optimal transport field. And I was like, oh, that seems to apply to what we are trying to do. And that's where the sort of like downhill idea came from, because it's like you propagate the information like forward or downhill, like as a gradient descent. And you don't want to be stuck in local optima or local optima, like just like with gradient descent, but like it seems to approximate this sort of like global global view optimization problem. So that's why I liked it. I wrote something about this there. But yeah, I think it's and yeah, one thing I will add is like it's actually not trivial even with a global view to find like the sort of like very optimum way. Like people have done it now, but it took them like a lot of time to do that, even when you have like a global view of the network, which is fun.
One thing we should do is run these simulations with the size of the current Ethereum network. So because that will change the duplicate rate, it will change the bandwidth efficiency of things, because once you actually size it to 15K nodes, so that would be times 10, I think, if I understood correctly. That would like give more opportunity. There would be more slack for duplicates to circulate, and that is where suppressing duplicates and bringing in some of the gossips of like techniques minimally would potentially help here.
So I had simulations with 50K nodes until my laptop was stolen, and I had to rerun the simulation with 1.5. but I originally did have this, and you see more drastic effects of RTT aware rules compared to like unaware ones, because yes, you have more opportunities to like spread like duplicates all over the network, and so that showed up as well.
Yeah. Okay. Cool. Yeah. One other thing is that we also have some tooling that computes RTT between nodes, specifically in the Ethereum network. So it's a more realistic approximation of the distribution that we have.
Nice.
And then on top of this, we're like through the work that I described, we're trying to analyze the graph so that then we can like put that we can cross both like both data sets.
Yes.
And actually get a understanding of effective RTT within the graph overlay.
That's what I want.
Yeah, we're getting there. We're getting there.
The sort of like better observability was like exactly this. Like, please, like I want the sort of like global topology of what we are dealing with, plus some like realistic RTT distribution, and then we can be a bit more confident. Because otherwise, I mean, you look like if you have the sort of like random, like log normal sort of like network, and you optimize for it, you end up being completely screwed if like the network changes and you are like into like you go into some like bimodal distribution or whatever. So for sure. No, that would be super useful. And as soon as we have data on this, I'll be happy to also like help like parsing through the data.
So
nice.
Yeah, cool. Good.
Okay, I think that's all. Thanks everyone.